Alright, so say for some crazy reason we want to calculate the terms of an ordinary simple annuity when the future value is known. And that is to say we have a monetary goal we'd like to reach and we want to know how long it's going to take to get us there. So in this case, how long will it take for $100 deposited at the end of each quarter to amount to $2,312.37 at 6% compounded quarterly? We know we're given the future value of an ordinary simple annuity because our payments are made at the end of the same interval as our conversion is made, quarter and quarterly. So from here, the formula that we want to use for the future value of an ordinary simple annuity is future value equals the payments made times 1 plus the interest rate raised to the power, raised to the power of n, which is the number of payments made, minus 1 divided by the same interest rate. So what we know from this and what we can plug into our formula is first the future value of $2312.37, the regular payment of $100, the interest rate of 6%, which is compounded quarterly. And for our purposes, that's 6% divided by 4 quarters, which is 1.5% per quarter. And we're looking for n. Okay, so now that we've got all the information from our question, which was staged and given to us, but you get the idea, we have our formula, which we're going to use, and we're going to fill in with the information that we've been given. So our interest rate is 6%, but because we are working quarterly, we will divide that 6% by 4, which will give us 1.5%. In turn, our interest for this equation will end up equaling 0.015. Okay, so now that I've got my formula filled out, you'll see that we have the future value is equal to the payment times 1 plus the interest rate, still raised to our power of n, which we're solving for, minus 1 divided by our interest rate. So from here, we're going to just follow through and isolate for n like normal. Okay, so let's start by doing that. In this case, we will begin by dividing out 100 because what we're looking at is 100 over 1. So let's get rid of that and bring it over to one side. That will give us 23.1237 is equal to 1.015. I added the 1 plus the interest rate, still raised to the power of n minus 1 divided by 0.015. So from here, I'm still looking to isolate n, so let's multiply everything by that denominator because we know that will reduce our fractions to a single linear term. So we multiply each side by our interest rate, and that leaves us with 0.346845 on this side. And on the right side, we still have our exponent, which is unknown, but nonetheless, safety brackets are always good, and it's still minus 1. So common sense is going to tell us to add 1 to both sides. Common sense and knowledge of algebra. So now we have 1.346845 is equal to 1.015 raised to the power of n. Oh, okay. So we're getting a little bit closer than we were when we started. So now that we have this right here, is basically all we want to look at, we're going to take the ln from both sides. So that is to say, that's a W, the natural logarithm of this question is the ln of either side. Okay, so never mind all that. But here we go. So we take ln 1.346845, and we take ln 1.015 raised to the power of n. This brings out our exponent, and we're left with the remaining linear equation. From this step, we can divide out our term here onto both sides, and that will give us an isolated n, which will be equal to ln 1.346845, and in this case you want to be as accurate as possible because you will get a better understanding and a better reading, divided by ln 1.015, which in turn gives us, used by our graphing calculator, n is equal to 19.9950. Otherwise, our terms are 20. So since we used that natural logarithm, ln, to bring out our n exponent, we have a number that equals our n terms, and that's 20. Since we're looking at a quarterly annuity, we can divide these 20 terms by the 4 quarters they consist of, and we're left with a 5-year-long annuity. And there you have it. So thanks for watching. I hope this helped, and I'll compute you later.